Hello and welcome to part 2 of Datatonic's video series on explainable AI. My name is Laurence, and in this video I'm going to go through an introductory guide to help get you started doing explainable AI and to highlight some of the key things you need to be thinking about if you want to make your explanations more meaningful. If you haven't seen part 1 of this video series already, where we discuss why you may need explainable AI and how it fits into your company's AI adoption framework, then I recommend you go watch that first. Otherwise, let's get into it. The first thing you need to be thinking about in explainable AI is approaching the problem with the right mindset. This diagrammatic flowchart shows a typical machine learning pipeline and is commonly how people approach the problem of explainable AI. First comes the data, then you do some processing, then model development, and finally, once you train your model, that's when people start thinking about explainability. However, if you're to do XAI properly, you need to be thinking about explainability right from the very beginning and at every stage of your project, not just retrospectively. Every decision you make will have an impact on the potential explainability of your final solution, so it's crucial that you're thinking about explainability when you're selecting your data, performing feature engineering, and choosing your ML model. If you don't do this, you risk making decisions that will ultimately make achieving explainability far harder or worse, just not possible. The next thing you need to be thinking about is who is your target audience. Now, there are a number of different target audiences that demand explainability, and key to this as well is that they will require different explanations as they ask different questions. There are multiple ways in which you can group audiences, but I'll go through how we like to do it. So we distinguish between 5 different types of audiences. First off, you have techies, researchers, developers, data scientists, which I assume if you're watching this video, you're most likely one of them. And these people are typically responsible for creating the ML model and developing the AI solution. Next, you have domain experts. We have a picture of a doctor here, but these can be experts from any domain that uses AI solutions. However, the key distinction is they lack the specific ML and AI technical background that the techies and developers might have. Next, you have end users. Now, these are people who are impacted by the output of the AI solution and usually don't have any influence on how the solution has been created. These people may be internal or external to your organization, such as members of the general public. Next up, you have management and executives who may be directly in charge of the teams developing the AI solutions, or they could sit higher up in the organization, or they could also be shareholders. And this group of people, they want to understand how the model will affect the business. The final group is legal and regulatory entities who want to make sure that the AI solution is compliant with the law and meets certain regulatory standards. So this leads us now to defining what constitutes a satisfactory explanation. And in order to do that, let's have a look at the types of questions that some of these audiences might ask. So you could have, for example, a model which is used to predict insurance premiums for members of the public. And a question that somebody may ask is, why is my insurance quote so high? I feel that I'm being unfairly treated. And a possible explanation as to why this is the case could be the number of claims you made in the last year falls outside 3 standard deviations from the mean. Our insurance quotes are linearly dependent on the number of claims made in the last year. Now, the problem with this explanation is that it uses maybe members of the public may not understand. For example, it talks about standard deviations and linear dependency. So a better explanation in this case would be, you have made 4 claims on your insurance in the last year, which puts you in the upper 1% of the demographic number of claims made in the last year. In our model, each claim made in the last year increases premiums by around 35%. Now, this explanation uses numbers and figures which are far more easy to grasp for people who don't deal day-to-day with data or statistical analytics. Another example, if a model was used in patient diagnosing, then a doctor quite rightly would want to understand how the decision-making process of the model. So one explanation could be, for this patient, heart rate, BPM, smoking flag, alcohol consumption, and pain location have the highest feature relevance scores, giving them a positive prediction. Now, this explanation is unsatisfactory because despite telling you which features were most important in making the decision about the patient's diagnosis, it does not tell the doctor anything about what the relationship between the features that led to the diagnosis. So a better explanation would be something like, our model shows the probability of a positive prediction is directly proportional to heart rate, BPM, and alcohol consumption in patients that have a positive smoking flag and pain location. So this explanation is actually describing the relationship between features which is driving the prediction. One final example, if a model was to be used by traders, they will want to, for example, be able to understand the risk that is inherent in the model. So a poor explanation which could lead to a risky application of a model could be, in training, 85% of the time, our model produced returns of over 20%. For the remaining 15% of the time, it returned losses of 35%. The model shorts aggressively in response to the social media word embedded feature. Now, this a more informative explanation would be something like, the model is very sensitive to the social media word embedded feature and alters the predicted output in response to sentiment from a list of key individuals. It is not possible to quantify risk due to the unpredictability of this feature. So this explanation tells us specifically about what about the word embedded feature is causing the variability in the model output, but it also acknowledges that full explainability was not possible in this case. So therefore, it's not possible to accurately quantify the risk for this model, and therefore, in this use case, the model shouldn't be used. So now we've discussed quite a bit about the mindset you need to adopt for XAI and ensuring that your audience is at the forefront of your thinking. But now let's look at some of the more practical aspects. And to begin with, we'll look at the data processing and feature engineering. Now there's one key message which I want to get across here, and that is when you're doing your feature engineering, you need to ask yourself the question, are the final features that I'm feeding into the model understandable to my target audience? So interpretability of a model extends beyond just the model itself, but also to the inputs that are going into the model. For example, you can have a very simple model whose behavior is fully explainable, but if you can't explain what the features represent, then it's impossible to produce explanations. I've listed here some feature engineering methods that lead to uninterpretable features. Some here are ones which may not come as a surprise to you, others may be less obvious. So, such as principal component analysis and embedded features are quite clearly not inherently interpretable features. Others may be less obvious. Proxy features, for example, what do we mean by these? So these are features that are actually just correlated to the driving features, which may or may not be represented in the feature table. And so the proxy features, when analyzing our model, are masking the real underlying relationships that are in the data. Another one which you might not have guessed is having too many features. So you could have only very simple raw features feeding directly into your model. However, if you have too many beyond the scale of what a human can comprehend, then again, you're going to make your task of achieving explainability very difficult. Moving on to model selection. Now there's a lot to talk about here, so we're only going to quickly go over at a higher level the different types of models that exist and the considerations you need to make when choosing your model. Broadly speaking, when it comes to explainability, there are two types of models. These are transparent models and black box models. Transparent models are inherently interpretable and they possess three core components, which we'll come on to in just a moment. Black box models, on the other hand, are not inherently interpretable and as a result require a different set of approaches when it comes to explaining them. Transparent models tend to include the more simple types of ML model, while black box models include all types of neural nets and ensemble methods, and they have the ability to discover more complex patterns in data in general. Now, the three properties of transparency are simulatability, decomposability, and algorithmic transparency. Simulatability is the ease at which the task being performed by the ML model can be replicated by a human. Decomposability, as the name suggests, is the ability to decompose a model into each of its constituent parts and to be able to explain each of them separately. And finally, algorithmic transparency is how well the model decision-making process is understood. Or mathematically, you can think of this property as the ability to navigate the loss space of the model via analytical methods, as opposed to heuristic ones like gradient descent. Here is a list of the main types of transparent models, and I'm sure you'll be familiar with most of these names. It's worth noting that different types of transparent models will obey the three properties of transparency to varying extents, and as a result will have varying levels of inherent interpretability. Now, as we mentioned before, our black box models possess none of these three properties, so instead we have to use indirect methods to try and interpret what is going on within the model. Broadly speaking, there are 6 different approaches to this challenge, dubbed post hoc techniques, and these aim to cast a light on the inner workings of the black box models. First off, we have text explanations, which provide a semantic mapping from a model's behavior into human understandable words and symbols. Visualizations are key in explaining difficult concepts to different audiences and form an essential part of almost any explanation. Explanations by example is where you provide specific examples that highlight key characteristics of the model, such as examples which highlight an output decision boundary. And this is a method which is very intuitive to humans, as it's a common way in which we provide everyday explanations. Local explanations is where we focus on a localized region within the model and approximate the complex space as a linear one. Once we've done this, we can then reason and interpret the linear region instead of dealing with the full complexity of the model. Feature importance looks at the input features to the model and assesses the individual impact of each feature to a model's predicted output before aggregating its results to determine overall contributions of the features to the model's predictions. And last but not least, we have model simplification, which is where we train a transparent model to try approximate the behavior of the original complex model, and then we focus our efforts on explaining the simpler model instead of dealing with the full complexity of the original model. So at this point, you may be wondering if explainability techniques exist for both transparent and black box models, then why can't we just use black box models all the time, as they are supposedly more accurate than transparent models? So this idea is commonly espoused as the accuracy-complexity trade-off, and it's the idea that your model can either be interpretable and transparent or complex and accurate, but nothing in between. The idea of the accuracy-complexity trade-off is very misleading in that for many common use cases of machine learning, transparent models are actually more than accurate enough to do the job. Now, post hoc techniques, which we just went through, aim to approach explainability by taking these more complex and more accurate models and making them more interpretable. However, what I want to stress here is that if explainability is a core goal from the outset of your project, then you should be using a transparent model and instead trying to make it more accurate. Black box models, despite with the aid of post hoc techniques, will never be fully interpretable. All the post hoc techniques we have mentioned do not give a full picture of the inner workings of the complex model, either because they work by explaining a simplified version of the model or because they only focus on cause and effect by varying different inputs to the model. So the key point is, if you can use a transparent model, use a transparent model. So to round up, let's quickly just recap what we've covered. In order to do XAI properly, you want to be thinking about explainability right from the outset of your project. You need to clearly have in mind who is the intended target audience is for your explanations, so that you can define what constitutes a meaningful explanation for them. When doing your feature engineering, try not to over-engineer and ensure that all your features are understandable to your target audience. Pick the right machine learning model for the job, which means if you can use a transparent model, use a transparent model. Only use a black box model as a last resort, and remember that if you do use a black box model, you will never be able to achieve full explainability. And finally, once you followed all these steps, you're in a good position to go and make some explanations. So, thank you for watching and take care.